Welcome back. I hope you were successful in finding some of the non-idealities of the LM741 op-amp. Let's go into the datasheet together and confirm your answers and maybe talk about some of the weird things you may or may not have found. Here's the LM741 operational amplifier datasheet. You'll see it's a general purpose op-amp and it's typically used in very common negative feedback circuits such as this non-inverting amplifier. Scrolling through the datasheet, we can see that the op-amp has two different packages that you can choose from, the LMC package and the NAB package. The op-amp itself has 8 pins, one of which is a no connect, so really only 7 pins. We have the typical ones we would expect, the inverting input, the non-inverting input, V plus and V minus as the power supply rails. We've got the output, and then we've got pins 1 and pins 5, which are known as the offset null pins. They're used to eliminate the offset voltage and balance the input voltage. So basically, you can completely eliminate the offset voltage by using these 2 pins. And what you do is you connect a resistor between the 2 pins and you adjust it accordingly until the output voltage is 0 when the 2 voltages on the input are equal to one another. So you can essentially get rid of the input offset voltage non-ideality, but it does take some tuning. Next, we see that the absolute maximum ratings of the op-amp for the LM741 specifically is plus or minus 22 volts on the supply voltage, power dissipation of 500 milliwatts, a differential input voltage of plus or minus 30 volts, and a general input voltage of plus or minus 15 volts, which should not exceed that of the power supply. We can short circuit the output continuously, which is really interesting, so we don't have to worry about accidentally short circuiting the output. And it seems like it works up to about 125 degrees Celsius. In terms of the recommended operating conditions, they recommend you always apply a differential supply voltage, plus or minus 10 volts, and that you don't operate the device greater than 125 degrees Celsius. In terms of the thermal resistance information, we get both the junction to ambient and also the junction to case thermal resistance, which is totally dependent on the type of package that you buy. This is pretty high thermal resistance. If you remember inside of the MOSFET lecture, we saw that a typical junction to ambient thermal resistance for a power MOSFET is about 3 times less than this number. Moving on to the most important part, which is the electrical characteristics section, we see at the very first parameter it labels as the input offset voltage. And it is typically about 1 millivolt. So you have to apply 1 millivolt across the 2 inputs in order to get 0 volts at the output. This is given at an ambient temperature of 25 degrees Celsius. If you operate it warmer than this, you will never see more than a 6 millivolt input offset voltage. So 6 times more is basically what they guarantee you'll never see greater than. You can adjust the input voltage, offset voltage range if it's within plus or minus 15 millivolts. Next is our input bias current. Let's take a look at that first. So the input bias current at 25 degrees Celsius is typically 80 nanoamps, but up to 500 nanoamps. And at various temperatures, it can get all the way up to 1.5 microamps, which is actually quite high. In terms of the difference between the 2 input bias currents, which is known as the input offset current, we see that the maximum is somewhere around 500 nanoamps. However, typically at 25 degrees Celsius, we can see it to be about 20 nanoamps. These are huge differences. The input resistance is somewhere between 300 kiloohms to 2 megaohms at 25 degrees Celsius, assuming a supply voltage of plus or minus 20 volts. Notice how it does not give you input capacitance or input impedance. This is the very first indication to you that this operational amplifier is not meant to be used in high-frequency applications. The input voltage range it's telling you is recommended to be about plus minus 12 to plus minus 13 volts. And the gain of the op-amp is going to be somewhere between 50,000 to 200,000. It's because it's this volts divided by millivolts, you have to add 1,000 to each one of these numbers. However, it looks like when you get a little bit hotter, the gain can go down to about 25,000. These are still pretty high, and it's still pretty good op-amp. The voltage swing goes up very close to the supply rails, but it doesn't actually hit the supply rails. So you can see if the supply is plus or minus 15 volts, the output voltage is not going to reach plus or minus 15 volts. So it will actually saturate before it gets to that value. Next, the output short circuit current is about 25 milliamps. Notice how it has not given you the output impedance of the operational amplifier. It's only given you the output short circuit current. Now you can figure out what that output impedance is from this current. However, it doesn't give it to you. Next is the common mode rejection ratio, which is typically 95 dB. That's very, very high, but it can get as low as 80 dB. And the power supply rejection ratio is about 86 dB to 96 dB. Typically, it doesn't give you a maximum. Later on inside of this data sheet, it will actually tell you how to make the power supply rejection ratio help you out a little bit more by applying bypass capacitors next to the operational amplifier such that they mitigate the noise before it even gets into the op-amp. The transient response is not really that important to us right now. The slew rate is 500 millivolts per microsecond, which is kind of slow for an op-amp, and it does draw about 1.7 to 2.8 milliamps of power just to operate, of current. And in power, that translates into between 50 to 100 milliwatts of power. Now, the rest of this is for different models of the same op-amp, so we can scroll down and go straight into the detailed description. So this op-amp is really complicated. It's got tons of BJTs internal to it, so many transistors. And it has various different features, which are really, really nice. But let's take a look at some of the things that we want to be careful about when using this. So it goes through a simple design of a non-inverting input and tells you how to use it. Notice how there's no capacitors or anything in here. This is yet another indication that this device is not meant to be used in a high-frequency application. The other one is that it did not tell us what the gain bandwidth product was. Notice how it actually doesn't have anything about bandwidth whatsoever. If you do go into the LM741A, it does tell you bandwidth, but it actually has a note here that says they calculated bandwidth by just using a random number, 0.35, and dividing it by the rise time of the op-amp, which is 0.25 microseconds or something similar to that. That is really a hand-wavy calculation, so you should know that this op-amp is not meant to be used in high-frequency applications. Next, it talks about layout guidelines, and it tells you to put capacitors next to the input to filter out the power supply noise so that you don't get it in the feedback, and it tells you how to run your traces and how to generally lay this out on a printed circuit board. And that's pretty much the end of the data sheet. There's no graphs, there's no tables of functions of all of those non-idealities as a function of temperature or supply voltage. It gives you the bare minimum information. This is really a general purpose op-amp. It's really only meant to be used for the super basic types of circuits that we've already learned. Now that we have all that information and we understand this a little bit better, let's go back and take a look at some potential interview questions related to real-world op-amps. The first practice question I like to give is this circuit. You've powered an LM741 and you've looked at the data sheet and decided to power it with plus 15 volts and minus 15 volts at the supply rail. And you've decided to ground both of the inputs. What is the output going to be? Now, this question is trying to test your knowledge of input offset voltage. We know that the input offset voltage is going to be some finite value greater than 0 millivolts based on what we've seen, and it's going to be typically 1 millivolt according to the data sheet. The gain of the op-amp is approximately 200,000 typically, so we would get 200 volts if we were to multiply the gain by the input offset voltage. However, we know that, of course, the output of the op-amp is limited to its supply voltage rails, so you could say that the answer is plus 15 volts. But an even better answer is that the output is probably going to be about plus 14 volts. And the reason why that is remember we talked about the fact that this specific op amp doesn't swing all the way to its top 15 volt supply voltage. It goes to about either 13 or 14 volts typically. So that's the answer to this specific question. If you don't remember the concept of input offset voltage, then you might accidentally say, oh, since the two inputs are exactly the same, then the output must be 0 volts. This clearly indicates to the interviewer that you've never worked with a real-world op-amp before and you don't understand the concept of input offset voltage. Next question. This is a little bit more complicated. Let's read the question together. Consider the below snippet from a section in the datasheet for a real-world operational amplifier, the LM741 Charlie. Assume that the op-amp is being operated in its worst-case scenario for all the below parameters and is being used in the following circuit shown below. Which parameter of this real-world op-amp will have the worst effect on the output voltage of the op-amp in comparison with an ideal one? So it's giving us two parameters, the input offset voltage, which we just talked about, and the input bias current. This is a really common question. Interviewers will ask you, what is the worst non-ideality inside of an op-amp? You should already know this. I talked about this in the last lecture. It is the input bias current. It's always going to be, most likely. But let's verify and make sure. So we talked about assuming that the op-amp is operated in its worst case scenario. That means that we can assume the input offset voltage is 7.5 volts and that the input bias current is 0.8 microamps. Take a look at what we're doing here. We've got plus or minus 20 volts on the LM741. We've got the output connected directly to the inverting input, meaning that this is a voltage follower. And we have a 1 mega ohm resistor in between Vin and the non-inverting input. So whatever the voltage we see at the non-inverting input minus the input offset voltage essentially is going to be the voltage at the output. So let's take a look. Because the output is connected directly back into the inverting input, the gain is just 1, right, of this entire circuit. It's a voltage follower. And therefore, the input offset voltage issue, which is 7.5 millivolts at the output, or at the input, is going to be exactly 7.5 millivolts at the output. So it's going to cause a 7.5 millivolt shift in the output voltage from what we actually want. But the input bias current is 0.8 microamps. 0.8 microamps is going to flow through this resistor from Vin. And it's going to cause a voltage drop across this resistor equal to V equals IR. And that's going to be 0.8 microamps multiplied by 1 mega ohm. And this is going to give you 0.8 volts. So if you have a 1 volt input at Vin, then there's going to be 0.2 volts at the non-inverting input. And then your output is going to be 0.2 volts minus 7.5 millivolts. So obviously, the much bigger impact is that of the input bias current. It causes a whole 0.8 volt differential between Vin and the non-inverting input, and thus V out in this specific case. So input bias current, much worse of an effect, especially when you have large resistors. Final practice question, and all the other practice questions are going to be inside of the resources that I've linked to. This is about common mode rejection ratio. The question that I'm going to pose to you is that in the ideal operational amplifier, you have infinite common mode rejection ratio, but in a real-world one, you have finite. Let's say we're operating the LM741 op-amp near a wall outlet, and we have a 60 Hz signal on the inverting input and a 60 Hz signal on the non-inverting input. They're exactly in phase, they're exactly the same amplitude, and they're going in. What is going to be the amplitude of the 60 Hz signal at the output? So if we take a look at 60 Hz on this common mode rejection ratio plot versus frequency, we see that the common mode rejection ratio at 60 Hz is going to be approximately 80 dB. So how do we actually convert dB into volts? The equation is that common mode rejection ratio equals 20 log 10 of the differential gain over the absolute value of the common mode gain. So if this is equal to 80 dB, then what that means is that log 10 of all that stuff is just going to equal 4, which means that 10 to the power of 4, which equals 10,000, is going to equal the difference between the differential gain and the common mode gain. So effectively, what we're going to be doing is amplifying the difference between these two 10,000 times better than we amplify the common between these two inputs. So whatever we have at the input here, we're going to divide it by 10,000 at the output. So if we have 1 volt sine wave at the input at 60 hertz, by the time it gets to the output, what's it going to be? It's going to be 100 microvolts. So it's going to be divided by a factor of 10,000. That's how dB works for CMRR. And by the way, this is exactly the same for the power supply rejection ratio. I hope that this lesson was useful for you in understanding the non-idealities of real-world operational amplifiers. There's a lot more information in the resources section. Please check it out. Next, we're going to move to one of my more favorite topics. Stay tuned.